Okay, let's go ahead and get started. So there's another problem set for you guys to pick up. This is the penultimate problem set, which will be followed next week by the ultimate problem set. So I'm very excited today because today we're going to start considering what is really my favorite part of this class. So over the next 2 weeks, what we're going to be doing is we're going to be developing an entirely new way of thinking about classical mechanics. So just to remind you a little bit about where we've been and where we're going in this course. This course started with a discussion of Lagrangian mechanics, which was a completely novel formulation of the equations of motion of a dynamical system as a minimization problem, where we saw that essentially any dynamical system subject to a few constraints, such as the fact that the system is holonomic and conservative, can be understood as a minimization problem via the action principle. And then, essentially, over the next month or so, we proceeded to use this framework to tackle all sorts of interesting problems, starting with the very simple, with harmonic oscillators and one-dimensional systems, before moving up to the more complicated problems of rigid body motion and generic n-dimensional systems. So, what I would like to do today is to start introducing what is known as the Hamiltonian formulation of classical mechanics. And the way that you should think of the Hamiltonian formulation of classical mechanics is that you should think of it as an alternative formulation of the rules of classical mechanics. So, when you were children, you learned the first way of formulating classical mechanics in terms of Newton's laws, or the Newtonian formulation. And then when you were young adults, at the beginning of the semester, you learned the Lagrangian formulation. And today, you are now passing into adulthood and learning what I consider to be perhaps the most elegant and conceptually beautiful formulation of mechanics, which is the Hamiltonian formulation. And at the end of this class, as we pass into our dotage, we will learn a fourth formulation of mechanics, which goes under the name of the Hamilton-Jacobi formulation. So I should also perhaps say just a few words to set the stage before diving into the details of Hamiltonian mechanics. So the first thing is that just as Lagrangian mechanics was completely identical to Newtonian mechanics, it was just a reformulation of the rules of Newtonian mechanics in a slightly different language. The Hamiltonian formulation is completely identical to the Newtonian and Lagrangian formulations. The equations of motion you derive are the same in any formulation of the theories of classical mechanics. Now, the advantage of the Lagrangian formulation is that it both had made things conceptually simpler because it allowed us to understand things like Noether's theorem and the relationship between symmetries and conserved quantities. But the Lagrangian formulation was also an extremely efficient machinery for computing equations of motion. And indeed, it was much, much simpler to compute equations of motion of complicated dynamical systems from a Lagrangian rather than from a Newtonian point of view. Now, the Hamiltonian formulation is just as or more powerful than the Lagrangian formulation as a conceptual tool for understanding mechanics. But I will be honest with you, it is not particularly useful for doing explicit computations of equations of motion of dynamical systems. So the Lagrangian formulation is really the gold standard for doing actual computations. You know, if I hand you a random mechanical system and say, find the equations of motion and study their solutions, you know, generally speaking, the Lagrangian formulation is going to be your best bet. But the advantage of the Hamiltonian formulation is that it really makes so much of the underlying structure of classical mechanics clear in a way that it is not entirely clear in the Lagrangian formulation. And because of that, the Hamiltonian formulation of classical mechanics is the formulation of classical mechanics that generalizes to quantum mechanics. So, you know, there's a reason why you've heard of a Hamiltonian before, and that's because, you know, you've already taken quantum mechanics and you've learned about Hamiltonians. But, you know, that was all probably reasonably ad hoc and did not make too much sense from you. So, for example, you learned that the Hamiltonian generates time evolution and is described by a certain differential operator, which is constructed, which acts on wave functions in quantum mechanics. But you didn't really understand why that was the case. And that's because there's a sense in which the way that you take physics courses as an undergraduate is ahistorical. And if there were any justice, you really would have taken this class before you ever took quantum mechanics. And so when you sat down in your quantum mechanics class and started trying to understand how to formulate the theories of quantum mechanics, you would have naturally started by thinking about the Hamiltonian formulation of classical mechanics, because it's this formulation which will generalize to quantum mechanics. And so, in a sense, I feel sorry for you, because you're going to be seeing so many formulas over the next 2 weeks, which are essentially identical to formulas that you've seen in quantum mechanics. And really, you should have seen them first in classical mechanics, and only then taken a quantum mechanics class and understood them from the quantum mechanical point of view. But of course, life being what it is, you know, we wouldn't want to make you wait until your last year of undergraduate to take quantum mechanics. So, you know, you have to get a jump start on it by taking quantum mechanics earlier. So that's probably enough, you know, philosophical blather. Let's go ahead and try and understand exactly what the Hamiltonian formulation of mechanics is. So let's consider some dynamical system. So consider a dynamical system with n degrees of freedom. So the dynamical variables will be qi, where I runs from 1 up to n. And let's imagine that the dynamics is governed by a Lagrangian, which, as usual, depends on those dynamical variables, their time derivatives, as well as some explicit time dependence. Then, a very long time ago, at the beginning of the semester, we defined the Hamiltonian H in the following way. It was the sum over I, pi, qi dot minus L, where pi was the derivative of the Lagrangian with respect to qi dot, and that was called the canonical momentum conjugate to the dynamical variable qi. So we have n dynamical variables and n conjugate momenta. And we saw that if the Lagrangian has no explicit time dependence, the Hamiltonian is a constant of motion. But in fact, the Hamiltonian is much more than that. So to understand what is so special about this expression for the Hamiltonian, what I would like you to do is consider this Hamiltonian, this formula for the Hamiltonian that I wrote, and imagine it not as a function of q, q dot, and t, but imagine it as a function of the momenta independent of the dynamical variables q. So imagine writing down this expression for the Hamiltonian, pi qi dot summed over I minus the Lagrangian, but don't let p be the canonical momentum. Just let it be some arbitrary n variables. So just think of it as a function of n variables pi along with the q's, the q dots, and time. And pi will just be another set of variables. Okay, so let's stare at that expression for a minute and see what we can understand from it. So the first thing that you notice is that if you take the derivative of the Hamiltonian with respect to one of the pi's, well, that just gives you qi dot because of that sum over pi qi dot. Okay, that's all well and good. What happens if you take the derivative of the Hamiltonian with respect to qi? Well, that's just minus the derivative of the Lagrangian with respect to qi. Because pi, now remember, we're treating as an independent variable, so it is independent of the qi's. And finally, the derivative of the Hamiltonian with respect to qi dot is the sum of two terms. We have a pi, and then we have minus dl by dqi dot. Okay, so let's stare, and then of course we have our fourth equation, which you will remember. Well, okay. So let's just stare at these three equations for a moment. So you can see that dh by dq dot vanishes if we take the pi's to be equal to dl by dqi dot. So if we plug in to this formula the usual expression for the canonical momenta, in other words, if we let pi be dl by dqi dot, then the partial derivative of h with respect to qi dot vanishes, and we can think of the Hamiltonian as a function of the pi's and the qi's, and not as a function of qi dot. So the Hamiltonian has no dependence on qi dot, but only on pi and qi. In other words, we can write the Hamiltonian as a function of pi and qi, and then the equations obeyed by the Hamiltonian are dh by dpi is equal to qi dot, and dh by dqi, well, what is that? That's minus dl by dqi, which, by the equations of motion, so remember that the Euler-Lagrange equations say that dl by dqi is the time derivative of dl by dqi dot, otherwise known as the time derivative of the momentum p. So that is minus pi dot. And so what we would like to do is the following. So we would like to think of the Hamiltonian as a function not of the q's and q dots, but as a function of pi, qi, as well potentially on time. And then the equations of motion are given by the 2n sets of differential equations, dH by dPi is equal to Qi dot, and dH by dQi is equal to minus Pi dot. And these are known as the Hamiltonian equations, or Hamilton's equations. And these equations are completely equivalent to the Euler-Lagrange equations, which are the equations of motion obeyed by a dynamical system. Indeed, we just derived them by imposing the Euler-Lagrange equation that dl by dq, sorry, there's no dot there, dl by dq is the time derivative of p. So this gives us a different way of thinking about the equations of motion of a dynamical system. So, in particular, let me just summarize what I think of as the Hamiltonian recipe for writing down Hamilton's equation for a dynamical system. So let's imagine that we start with a system which has a Lagrangian that is a function of the variables qi along with their time derivatives. We define the canonical momentum p to be the derivative of the Lagrangian with respect to qi dot. And then we define the Hamiltonian to be the sum over I, pi qi dot minus L. And then we use the formula for the canonical momentum to write qi dot as a function of pi and qi. And then we use this expression to write h as a function of pi, qi, and time. And in particular, we eliminate all of the dependence on q dot. We just write it in terms of pi's, qi's, and time. And then the equations of motion of the system are Hamilton's equations. dH by dPi is qi dot, and dH by dQi is equal to minus pi dot. You'll notice that I'm a little sloppy about whether I write indices upper or lower. If I were being mathematically precise, I would need to be careful about whether I have upper or lower indices, but I will not be so precise in this class. So for the purposes of this class, it does not matter whether I write these expressions with upper or lower indices. Although, in my mind, I have reasons why for everything I do, but those reasons are not important to you. So, are there any questions on this Hamiltonian recipe so far? Now, at this point, I should mention one mistake that people always make. So it is a very common thing a problem that you will be asked to solve again and again in this class is the problem where I give you a Lagrangian and I ask you to write down the Hamiltonian and the Hamiltonian equations of motion. And the problem that people often run into is they forget step 4 and they leave in some explicit dependence on q dot, and then they get very confused and make all sorts of mistakes. So it's very important in the formulation of Hamiltonian mechanics that we think of the Hamiltonian as a function of P and Q rather than Q and Q dot. So the Lagrangian is regarded as a function of Q and Q dot, but the Hamiltonian is regarded as a function of P and Q. And it's only when I regard the Hamiltonian as a function of P and Q that I can write the equations of motion in this very nice way as Hamilton's equations. So why is this a nice thing to do? So the first comment that I would like to make, so any questions before I continue? So the first comment that I would like to make is that this formulation is completely equivalent to the Lagrangian formulation. And in particular, the Hamiltonian equations of motion are completely identical to the Euler-Lagrange equations. So the first thing to note is that the Euler-Lagrange equations, so these are the Hamiltonian equations here. The Euler-Lagrange equations are a set of n second-order differential equations. So we have n second-order differential equations. Whereas the Hamilton's equations are a set of 2n equations, because in these expressions here, I runs from 1 up to n, and there's one equation for the qi dots and another equation for the pi dots. So they're 2n equations, but they're 2n first-order differential equations. And as you may remember from your differential equations class, you can always think of a second-order differential equation as a pair of first-order differential equations. Is that familiar to you from your differential equations class? All you do is you think, so let's say you have a differential equation for y as a function of x. You have y double prime, y prime, and x. And then you could think of y prime as a different variable, call it p, and then you would have two equations, one that says y prime equals p, and another equation in terms of p, p prime, and x. So that's exactly what we're doing here. So conceptually, the formulations are completely equivalent. And in particular, there's the exact same amount of initial data required to specify a solution. So in the Euler-Lagrange equations, you have n second-order differential equations, so you need 2n pieces of initial data, the initial positions and their time derivatives. In the Hamiltonian formulation, you have 2n first-order differential equations, so you need 2n pieces of initial data, the initial values of the qi's and the initial values of the pi's. Same initial data, just a different way of writing it. So what's the big deal, then, about the Hamiltonian formulation? Well, the big deal is that there are many things that are conceptually clearer in the Hamiltonian formulation. In particular, the Hamiltonian formulation treats the positions qi and the momenta pi on equal footing. So whereas in the Lagrangian formulation, the QIs were the basic variables, and the PIs were just some constants of motion which are constructed out of the QIs and their time derivatives. In the Hamiltonian formulation, these different 2n quantities are treated on completely equal footing. And that makes many things about the properties of dynamical systems much clearer. So in order to describe this, what I would like to do now is introduce a bit more what I suppose is mathematical terminology. It's just some language that people use to describe the dynamics of systems in the Hamiltonian formulation. And in fact, many of the words that I use will already be familiar to you from your quantum mechanics classes. But before I proceed to do that, are there any questions? Okay. So let me first start with the definition. So we're used to thinking of the QIs as living in some sort of configuration space, which is some sort of n-dimensional space that describes the possible set of states of the system. So that's the basic object that one considers in the Lagrangian formulation of mechanics. And the basic object of the Hamiltonian formulations is the 2n dimensional space of QIs and PIs. And that is known as the phase space. And the point is that if you uniquely specify a point in phase space, you uniquely specify the state of the system. So a point in phase space uniquely specifies the state of the system. And the Hamiltonian is a function of points in phase space. So it's a function of possible states of the system. And here's the basic idea. So in your vector calculus classes, you are used to thinking of a three-dimensional vector as a three-component object. And in an n-dimensional space, you can think of an n-component vector. And in a 2n-dimensional space, you can think of a 2n-component vector. And so we think of the set of partial derivatives, dh by dpi and dh by dqi, as a 2n component vector living on this phase space. And it's the vector whose components are given by the derivatives of the QIs and PIs, which are the coordinates of phase space. And you have a name for a vector whose components are given by the derivatives of some function. It's a gradient vector. So it's a gradient vector. And what then are the equations of motion? So the equations of motion say that qi dot and pi dot. So the time derivative of the position and momenta, thought of as points on the phase space, are just given by this vector. So dh by dpi and dh by dqi. And there's a minus sign right here, so we could put a minus sign here. And if you wanted to think of this vector a little more precisely as a gradient vector, you should really think of it not as a gradient vector, but what you obtain by taking the gradient vector and rotating it by 90 degrees. So let me be a little more precise. So the vector h, so the function h defines the gradient vector. So we could think of, so if the qi's and the pi's are the coordinates on phase space, you could think of dh by dqi and dh by dpi as a gradient vector. And then the vector dh by dpi and minus dh by dqi is the vector that's found by switching the two components and putting a minus sign on one of them. And now, if you were just dealing with two-dimensional vectors, that procedure would just mean that you're rotating the vector by 90 degrees to the right. So that vector is found by rotating the gradient 90 degrees to the right. I guess I mean clockwise, don't I? I mean, who the hell knows? It's rotating at 90 degrees. Yeah, it's just a sign error. It's not my job to keep track of sign errors. I just teach the class. It's your job to keep track of sign errors. Let's see. If you start with the one that points in the y-axis, the 1, 0, then 0 minus 1, yeah, it's clockwise. So to the right. That's what right means, right? Because, you take this thing, you go to the right. Okay, it's clockwise. Clockwise. Okay, you want to call it clockwise? We'll call it clockwise. Fine. It's clockwise. Okay. So, now, so what does that mean? That means that you start with a Hamiltonian, which is a function on phase space. And if you want to ask how the system evolves in time, you take the gradient of this Hamiltonian function. That's a vector. You rotate the vector at 90 degrees, and the system flows in that direction, which is generated by that vector. Did you guys see gradient flow in your, you didn't see gradient flow in your multivariable calculus class? Well, this is very similar to what's known as gradient flow. So if we wanted a picture in our mind to keep in mind when we think about the Hamiltonian flow of the system, you could imagine your phase space. That's not a very good phase space. We could imagine our phase space as some two-dimensional space. So here, the vertical axis would be P, and the horizontal axis would be Q. And then your Hamiltonian would be some function on the phase space. Now, because it's some some function that is a function of points on the plane in this case. So an easy way of thinking of it is drawing the lines of constant h. So let's say that h is q squared plus p squared. That would be the simplest possible case. And in fact, let's even make it simpler. Let's write it as 1/2 p squared plus q squared. So in that case, the lines of constant h would be circles. The gradient of the Hamiltonian would be the vector which points radially. So the gradient would be a vector that points radially. And the vector field that generates the flow dh by dp minus dh by dq is found by rotating that 90 degrees clockwise. So that would point in this direction. And then the motion of the system is found by setting q dot p dot to be dh by dp minus dh by dq, which says that the time evolution in q and p just points in the direction of this vector, which is perpendicular to the gradient vector, which in this case is very easy to compute. It's just p minus q, which, as you can check, is indeed just that vector that I have drawn here, which moves you along lines of constant h. So one thing you can see here is that if the Hamiltonian is time independent, this gradient flow, by definition, moves you along lines of constant h. It had to work out that way. H was a constant of motion in that case. And indeed, if you look at this formula for the Hamiltonian that I wrote down, this is precisely the Hamiltonian for a simple harmonic oscillator with frequency 1. You'll remember I assigned you a problem on one of your earlier problem sets where you computed the Hamiltonian of the simple harmonic oscillator and you studied its phase space, and you saw indeed that the lines of constant h were given by circles on phase space. And so this Hamiltonian formulation gives you a very geometric way of thinking about the evolution of the dynamics of the system as a first-order evolution on phase space, which is generated by gradient flow. And so sometimes there's a set of words that we associate it with this. So the differential equation qi dot pi dot is given by dh by dp minus dh by dq is sometimes referred to as Hamiltonian flow. The important word here is flow, because you can think of the time evolution of the system as a flow on phase space which is generated by the Hamiltonian. You specify one function of q and p, that is the Hamiltonian, and you write down the first-order differential equation which describes how the system flows along curves of constant h. So you can think of the dynamics as a flow on phase space. Now, what I would like to do is just introduce a little bit of syntax here. I would like to introduce a few mathematical words. I introduce them not because I will be using them for the rest of the semester, or indeed ever again this semester, probably. But instead, I introduce them because they're words that people use all of the time, and if someone says them to you, I don't want you to get scared. So I'm just going to introduce a little bit of what is the mathematical language associated with Hamiltonian mechanics. So are there any questions, however, before I continue? Yes?
What would a second-order evolution be?
One that's given by a second-order differential equation. But the lovely thing about mechanics is that any mechanical system with a Hamiltonian formulation is given by a first-order differential equation on phase space. And that differential equation essentially says the time derivative of the point in phase space is equal to the vector perpendicular to the gradient of the Hamiltonian. Now, there's a bit of formal mathematical words that people associate with this. So rather than writing Q's and P's everywhere, if I wanted to, I could think of the Q's and P's rather than as separate objects. I could think of them, I could just define one collective coordinate on phase space. So formally, rather than thinking of Q and P as separate objects with an index that runs from 1 up to n, I could define a coordinate on phase space. Let's call it, say, x mu, where mu is an index that runs from 1 up to 2n. And if mu is something between 1 and n, then x will just be equal to q. And if mu is between n plus 1 and 2n, then x will just be equal to p. So x of I plus n will be equal to pi. So this would be a collective coordinate on phase space given by the q's and p's. So that's just a fancy way of saying that I could package together the q's and p's into a single coordinate that I'll call x. So we could define a coordinate on phase space, which is given by either q or p, and we can also define a 2n by 2n matrix on phase space that I'll call omega. Now, a matrix is something with two indices, so it'll be an omega with two indices, mu and nu, where mu and nu run from 1 up to 2n. And I'll define it such that omega ij is equal to 0, where I and j run from 1 up to n. Omega I n plus j is equal to delta ij. Omega I plus n j is equal to minus delta ij. And omega I plus n j plus n is equal to 0, where I and j run from 1 up to n. So another way of saying that, of course, is that omega is the 2n by 2n matrix whose block diagonal form is given by 0, minus 1, 1, and 0. So it's a 2n by 2n matrix, which if you wrote it in n by n block form would be given by 0, minus 1, 1, 0. And then the equations of motion take the following very simple form. They're given by x dot mu is the sum over nu omega mu nu dh by dx nu. And I encourage you to check that when mu is between 1 and n, this says that qi dot is equal to dh by dpi, and likewise when mu runs from n plus 1 up to 2n, it says that pi dot is minus dh by dqi. So this is just a very efficient packaging of, this is just a very compact packaging of the Hamiltonian equations of motion, which literally say that you take the gradient of h on phase space, you multiply it by this matrix, and you set that equal to x dot. And this matrix that I've called omega is the thing that implements the rotation by 90 degrees clockwise. And so this matrix actually has a special name. So the matrix omega mu nu has a name, and it is known as the symplectic structure of phase space. In particular, you can check that this matrix has the following property, that as an n by n matrix, it is equal to minus its transpose. Or, put more simply, it's antisymmetric. So now, if you were to go over to the math department and you were to tell one of your friends in the math department that you're studying classical mechanics, here's what they would think you were saying. So if you go up to a mathematician and you say, hi, I study classical mechanics, then this is what they will think that you mean when you say you study classical mechanics. So mathematically, a mechanical system or a dynamical system is a phase space which can be described by some coordinates x mu along with two objects. A function, which is the Hamiltonian on those coordinates, thought of as a function of phase space, and a symplectic structure, which is to say an antisymmetric 2n by 2n matrix. Now, of course, this matrix, so in the description that I gave above, the symplectic structure was this very simple 2n by 2n matrix, 0, 1, minus 1, 0. But as we will see later in this course, there are other ways of formulating Hamiltonian mechanics where the symplectic structure is more complicated, although we won't use the word symplectic structure. And so generally, to a mathematician, a dynamical system is a phase space with a function and a symplectic structure. And indeed, for those of you who have seen it, this symplectic structure is in fact what is known as a differential form. It's called a two-form. And all of the mathematics that people use to study the mathematics of classical systems follows from this basic starting point, that you have a function and that you have this two-form that people call the symplectic structure that satisfies some properties. So, if you were taking a mathematical class on dynamical systems, the first day of class would probably start with the definition of a mechanical system as a 2n dimensional space along with a function and a symplectic structure. Then they would take it from there. And many of the quite beautiful results in classical mechanics are indeed derived by starting with those assumptions. So, it is not the case that we will talk about symplectic structures in this class, but it is the case that I think it's a language that you should at least encounter once or twice in your life, so that if someone brings it up, you won't be offended. Are there any questions before I continue? Yes. Well, It would mean, no, the Hamiltonian would be the same, but the relationships between the Q's and the P's would be different.
So would it be like a dynamical system?
No, it would be a dynamical system, but would it be a dynamical system? So let's put it this way. One of the things that was great about the Lagrangian formulation of mechanics was that you could write down the equations of motion using whatever dynamical variables you like. And you could start with some QIs and transform to some other big QIs, and that would all be hunky-dory. And the physics would be independent. Now, it turns out that the set of so then you ask, well, now we have a formulation where we treat the Q's and P's on equal footing. So can I do transformations that mix Q's with P's? And the answer is not all. The answer is yes, but not always. And the not always comes because you need to preserve this thing called the symplectic structure. So this is the sort of so far in this class we've only considered symmetries where the coordinates transform to coordinates. But we are going to, in this class, start considering symmetries where coordinates mix with momenta. These are known as canonical transformations, and we will spend plenty of time studying them, where we'll come back and answer in much greater detail your questions. But another way of answering your question is that if your symplectic structure is not a constant, you could always go to a different coordinate system where it looks like a constant. But I'm not going to prove that to you. Okay. You had a question?
Does the symplectic structure have anything to do with the following equation?
No. You'll see. Yeah. Pauli matrices. Well, I mean, not really. No. Everything has to do with everything else. But yes, we'll understand all of that stuff in much greater detail. I mean, the Pauli matrices arise because you're studying angular momentum algebra. You can study the algebra in, one of the things that's a real shame is that you encountered the angular momentum algebra first in your quantum mechanics class before encountering it in your classical mechanics class. One of the things that we'll do, one of the things that you'll do on the next problem set is derive the angular momentum algebra in phase space using classical mechanics. So that's something that we will discuss. There was a question over here. Yes.
Yeah, in quantum mechanics, we learned about you have to have a complete set of conditions, complete set of conditions in order to describe state. And so for each different set of conditions observables that you choose, would you have a different symplectic structure?
Essentially, well, it depends on you would have a different coordinate system, and the symplectic structure would look different in different coordinate systems. Just like if you have a matrix, you can describe that matrix in different coordinate systems by conjugating it with respect to a rotation matrix. Here, you would want a matrix with what's called a symplectic matrix transformation rather than a rotation, but it's the same basic idea. So I might ask you to defer the questions about quantum mechanics, because later, probably not this lecture, but next lecture, and certainly the following lecture, we will see that the Hamiltonian formulation is incredibly similar to what you've seen in quantum mechanics. And essentially, all that you've done in your quantum mechanics classes is take equations in Hamiltonian mechanics and rewrite them in some mysterious way. Are there any other questions, however? I didn't mean to tell you can't ask questions about quantum mechanics, but I am telling you that the answer may very well be just wait till next class. Free to ask. I mean, you can ask whatever you want. Any other questions? Okay. So enough of the boring mathematics. Let's go ahead and do a couple examples, just to get used to the flavor of Hamiltonian mechanics. So let's consider the only example that I ever can remember all of the signs to. Let's consider a pendulum. So we have a mass of length L, And the dynamical variable theta will describe the angle that this pendulum makes with vertical. And as you may remember, the Lagrangian is a kinetic energy plus a potential energy, the kinetic energy being 1/2 L squared m theta dot squared, and the potential energy being mgl cosine theta. So let's go ahead and turn the Hamiltonian crank to compute the Hamiltonian of the system. So step one, what was step one? I forget what step one was. Step one was compute the momentum conjugate to the dynamical variable theta. So let's call that P sub theta. That's the derivative of the Lagrangian with respect to theta dot. Okay, that was easy enough. Step two is to write down the Hamiltonian, which is P theta theta dot minus the Lagrangian, which was 1/2 L squared m theta dot squared plus mgl cosine theta. Step three is to write the theta dot in terms of the canonical momentum p theta. Now, of course, in general, theta dot could depend both on p and theta, but this is a very simple example where theta dot depends only on p. And step four is to write the Hamiltonian as a function of p and theta, but not theta dot. So let's go ahead and do that. So we have p times theta dot, which was p over m L squared, minus 1/2 L squared m times theta dot squared, which was p over m L squared squared, plus mgl cosine theta, which you can see the first term is p squared over m L squared, and the second term here is 1/2 p squared over m L squared. So we get 1/2 p squared over m L squared minus mgl cosine theta. So finally, we write down the equations of motion. So theta dot is dh by dp, which is p over m L squared, and p dot is minus dh by d theta, which is minus mgl sine theta. There are three minus signs there. One is a minus that comes from p dot is minus dh by dq. The other is this minus sign here. The third is the minus sign that arises when you take the derivative of a cosine. So if you wanted to, you could then go ahead and check that this is completely equivalent to the Euler-Lagrange equation that comes from the Lagrangian. So let's do that. So let's take the time derivative of this equation. So theta double dot is 1 over ml squared p dot, which, if we plug in that expression for p dot, is minus g over L sine theta, which is exactly the Euler-Lagrange equation for the pendulum. Okay. So that was a very simple system where we were able to check very explicitly that the Hamiltonian and Lagrangian formulations were equivalent. Are there any questions on that? So let's maybe do a slightly more sophisticated example. So let's consider a bead moving on a wire. So I remember at the very beginning of this class, I wrote down the equation of motion for a bead moving on a wire of arbitrary shape, where y was equal to some function of x. It's late in the day, so let's consider a simpler example where the bead is moving on a parabolic wire. Okay, so what's the Lagrangian? Well, it's 1/2 m x dot squared plus y dot squared minus mgy. Or, if we wish to treat x as our dynamical variable, we can use the fact that y dot is x times x dot. Is there a question over there? Okay. So that means that the Lagrangian is m over 2 times 1 plus x squared times x dot squared minus 1/2 mg x squared. Okay, so let's compute the Hamiltonian equation of motion. So the momentum p conjugate to x is the derivative of the Lagrangian with respect to x dot, which is m times 1 plus x squared x dot. Here we see that the momentum is not just proportional to x dot, but also has some dependence on x. So this is a theme that we will return to again and again. I remind you, as we've emphasized before, that the canonical momentum is not necessarily the same as the mass times the velocity. It could have some other more complicated dependence on the dynamical variables. So the Hamiltonian is x dot p minus the Lagrangian. And we write that Hamiltonian in terms of x and p by using the expression for the velocity x dot in terms of x and p, which is p over m times 1 plus x squared. And plugging that in to our expression for the Hamiltonian, we have the first term is p squared over m times 1 plus x squared minus m over 2 times 1 plus x squared times p over m times 1 plus x squared squared plus 1/2 mgx squared.
It's much easier to simplify the h from the beginning.
Yeah, well, this is not so hard. This is then just p squared over 2m times 1 plus x squared. Again, we see that there's in this term here, there's an overall 1 over 1 plus x squared and 1 over m, and the only difference between these first two terms is that there's a 1/2 in front of the second term. So subtracting the two, we get p squared over 2m times 1 plus x squared plus 1/2 mg x squared. And this Hamiltonian is now written in terms of p and x, so we could then go ahead and compute the equations of motion by setting x dot to be equal to dh by dp, which would be p over m times 1 plus x squared. And p dot is minus dh by dx, which in this case will be a little more complicated because both the kinetic and the potential energy in this case have a dependence on x. So there'll be a term which is minus p squared over 2m times 1 plus x squared squared, and then there'll be a 2x in the numerator coming from the derivative of 1 plus x squared, and now, and there's an overall minus sign, yeah, so minus mgx. And these are the equations of motion of the system. And if you like, I invite you to go back to the beginning of the semester when we wrote down the Euler-Lagrange equations for the system and check that these Hamiltonian equations are equivalent to the Euler-Lagrange equations. Now, of course, it had to be the case that these were equivalent. Yes. Oh, sorry. It had to be the case that these are equivalent. The Hamiltonian and Lagrangian methods are completely equivalent to one another, but nevertheless, it's good to check. So, if we'd like to understand the dynamics of the system, now, it's sort of hard to just look at these two expressions for x dot and p dot and understand exactly what the dynamics of the system looks like. So it's useful to draw the lines of constant h on the xp plane. So, for example, in this case, what was the Hamiltonian? The Hamiltonian was p squared over 2m times 1 plus x squared plus 1/2 mgx squared. So here, if I let x be the horizontal axis and p be the vertical axis, then what do the lines of constant h look like? Well, near x equals 0, the Hamiltonian looks like a constant times p squared plus a constant times x squared. So we'll just have ellipses. So there'll be some sort of ellipses like that. And at larger values of x squared, so first of all, near p equals 0, we'll continue to have this sort of elliptical behavior. But in fact, at larger values of x, it turns out that there's sort of dimples that arise when you graph the lines of constant h. So I'll leave it to you to verify that for yourselves. But there are these sort of dimples that appear. And the dynamics of the system just says that x dot and p dot is given by the vector, which is found by taking the gradient of this Hamiltonian and rotating it by 90 degrees. And that is just the vector which points parallel to these lines of constant h. Sorry, these are not very good vectors. So, I should probably make one more. Are there any questions on that derivation before I continue? So this week on your problem set, you'll get plenty of chances to flex your mental muscles in deriving the Hamiltonian equations for various simple systems. But I should probably make one comment, which is that although Hamilton's equations are identical to the Euler-Lagrange equations, and are not particularly useful for writing down equations of motion explicitly. In particular, in the previous two examples that I worked out, you saw that you could have just as easily just written down the Euler-Lagrange equations rather than trying to write down Hamilton's equations. And so even though the Hamilton's equations aren't particularly useful for writing down the equations of motion explicitly, there are many instances where Hamilton's equations are conceptually clearer. So there are many conceptual advantages. And they all stem from the fact that in the Hamiltonian formulation of mechanics, we're using a formulation where the positions and momenta are treated on equal footing. And this has implications not just for classical mechanics, but for quantum mechanics as well. So, for example, in your studies of the quantum mechanics of a free particle or a harmonic oscillator, you probably encountered the fact that you could use momentum space basis for the wave functions rather than a position space basis. Did you guys see that in your quantum mechanics class? Yes. Okay. And so, for example, the free space, for a free particle, the position space basis is given by delta functions in position, and the momentum space basis is given by wave functions, which are plane waves in position space. So, this fact that you can work in whatever basis is convenient in quantum mechanics really stems from the fact that quantum mechanics, as you have seen it, is formulated based on a formulation of classical mechanics, where momenta and positions are treated on equal footing. And so this is something that we will begin to explore next class. I don't have quite enough time to introduce the next subject that I would like to. So probably rather than trying to squeeze it into the last 6 minutes I have left, maybe I should just pause and see if there are any questions. No questions? Yes.
In Lagrangian mechanics, we had a way to deal with systems where energy wasn't necessarily conserved.
Yes.
Is there a way to deal with that in this formula?
Absolutely. Absolutely. So the Hamiltonian, although I have been sometimes dropping the t dependence, also has an explicit dependence on time. So just take the Hamiltonian to depend on time. And indeed, you may remember that the total time dependence of the Hamiltonian was equal to the explicit time dependence of the Lagrangian. So if the Hamiltonian is independent of time, then has no explicit dependence on time. Yes. So even in quantum mechanics, if you want to study a system with a time-dependent potential, you just write down a time-dependent Hamiltonian, and you proceed exactly as you would for a Hamiltonian without time dependence. So yes, this works just as well for systems with time dependence explicitly.
Do you have a P dot and a Q dot that are explicitly time dependent? Does that necessarily imply that energy is not conserved?
So P dot and Q, P and Q are always functions of time. But their time dependence is determined by the equation of motion. Q dot is dH by dP, and P dot is minus dH by dQ. Here, let's work this out a little more explicitly. So, for example, if the Hamiltonian has no explicit dependence on time, then let's compute the total time derivative of the Hamiltonian. So obviously the partial time derivative of the Hamiltonian vanishes because it has no explicit dependence on time. And what is the total time derivative? Well, it's the sum of two terms. So P and Q depend on time explicitly. And so we have dH by dP times Q dot plus dH by dQ times P dot, which, using the Hamiltonian equations of motion, is dH by dP times dH by dQ minus dH by dQ times dH, what am I doing here? dH by dP. God damn it. This is why you should never improvise. dH by dQ times Q dot, dH by dP times P dot. So that's dH. Well, okay, I got it right, even though I wrote them in the wrong order. which is equal to 0. So you can see that P and Q, of course, do have some dependence on time, but because that time dependent, if you have a solution to the equations of motion, where Q dot and P dot are given by the solutions to Hamilton's equations, then H will be time independent if it has no explicit time dependence. So hopefully that answers your question. Okay. I mean, we did this computation in the beginning of the semester. We didn't use P's and Q's. We used Q's and Q dots, but it's the exact same computation. Any other questions? Okay, if there are no other questions, I'll see you on Thursday. And there's another problem set for you guys to pick up if you haven't picked it up yet. It's due next Monday.